happening. So, last week I gave you guys, over the course of this chapter, I've been giving you guys a little bit more to deal with as we've gone on. We talked about positioning, we talked about displacement, then we talked about how position and displacement change. As position and displacement change, then now we start talking about concepts of velocity. We graphed displacement time graphs. We found out that the slope was equal to the slope of a position time graph or a displacement time graph was equal to velocity. Then we started talking about how velocities change, which led us to the ideas of acceleration. Then we looked at the velocity time graphs, and we could see how a velocity time graph could give us both accelerations. Slope of a velocity time graph is the acceleration. And I tried to convince you that we could find displacement by finding the area underneath the curve. I gave you the 4 big kinematic equations. Those are really the only ones that you'll ever use in kinematics. I mean, the concept or the way they get applied gets slightly more difficult as you go on. As you'll see next year, you're going to talk about relative velocities and stuff like that, and things are going to get a little bit messier. But the fundamental equations all stay the same. The ideas behind how accelerations are related to velocities, displacements, and times are all still the same. The last 2 lessons that we're going to go through, the first of which we're going to do today, looks at a very particular kind of acceleration. This is an acceleration that you're all intimately familiar with because you've all fallen before, or you've dropped things, or you've thrown things, and this is the acceleration due to gravity. The purpose of the lab was to try and find this value. I'll give it to you again because I think we talked about it once already, and one of you even said that you looked at it in middle school. The acceleration due to gravity is 9.81 meters per second squared. Now, what does that actually mean? Connor.
Well, it's an acceleration, so you had an object that was not moving.
My orange.
Yeah, for example. And you released what was holding it up.
My fingers.
Yes. And you let it drop.
Okay.
From that point on, once you release that and there's nothing holding it up, gravity immediately takes it and accelerates it in 9.81 meters per second squared.
Yeah, so that means every second it's falling, it's going 9.81 meters per second faster. So that's, and which we've talked about before. That's what when we talk about accelerations. If you're traveling, if your acceleration is 3 meters per second, every second you're going 3 meters per second faster, right? Do we remember this? So after 1 second, you're going 3 meters per second. After 2 seconds, you're going. After 3 seconds, you're going 9, because 9 is 3 more than 6, right? So this is fundamentally the same thing. Every second of time that passes, you want to be, or your speed will be increasing by 9.81 meters per second. Hey, Betty, what's up? No worries. Kind of, sort of, not really. Well, the last period on a Friday with a prep, I'm getting out of here pretty quick. You betcha. Okay, thank you. Bye. My daughter getting me out of stuff again. Except gravity always accelerates which way?
Towards the Earth.
Towards the surface of the Earth, or towards the center of the Earth. Okay? Always down. Now, this 9.81 meters per second squared, this is not a universal gravitational acceleration. Do we know what gravity is dependent on? Yeah? The size of the planet. No, gravity does not depend on the atmosphere. Depends on the size of the planet / moon / star. What I'm trying to get you to see is like these objects are large. The acceleration due to gravity depends on how massive, not the object you're dropping is, but the mass of the object you're dropping things onto. So our Earth has an incredible mass. It's huge. I think I even give you that value. 5.98 times 10 to the 24 kilograms. We live on a relatively large hunk of rock. I mean, things get larger from here. So this is true. This acceleration due to gravity is true on Earth. Yes, Manuel.
Does altitude affect gravity on the Earth?
Technically, yes. Practically, no. So our next chapter is going to be on dynamics. So we'll look at forces. One of the forces that we'll look at in more detail is the force of gravity that causes the acceleration due to gravity. And I'll show you the relationship for the force of gravity and how objects with masses interact with each other. And you're going to see that in there is a term that takes into account how far apart the objects are. Because it makes sense that altitude would matter, right? Like you go way out into space, you're not going to feel the gravitational pull of the Earth. But as you get closer to Earth, you're going to start to feel more of that gravitational pull. So altitude has to deal with it somehow. But within even a couple hundred kilometers of the surface of Earth, you're not going to notice a measurable difference. Even on the surface of Earth, there are places where it's technically different gravity strengths depending on what the Earth is made of underneath your feet. Like if you could pull up a map of gravitational strength on the surface of the planet, and it's not the same everywhere. But the differences are so minute, you would never practically notice it. It's not like you'd trip in Idaho and be like, I didn't fall as fast. That's weird. Because it's the differences are so small. Your iPhone might catch it. Like the accelerometers in your phones are pretty delicate instruments. But you would never notice it. Yeah. And then Luis.
Can other objects have like their own gravitational pull?
Anything with mass has a gravitational pull.
Okay, but something like this would be so small that
You'd never notice it. Right. Luis.
Doesn't gravity change like how time passes? For example, in space, the time passes like slower than the Earth.
Actually, yes. We'll talk about that in the dynamics chapter. And that's the video I told you I told you about a video yesterday that I'm going to show you eventually. We'll talk about how gravity actually warps. It's not just time, but like actual space. Like you can see objects, like you can look at our sun and see stars behind our sun that aren't actually where you see them. They're actually behind the sun. You just see the light bending around the sun because gravity can warp both space and time. It's weird, but it's a thing. But for the sake of this chapter, all we want to focus on is how gravity accelerates objects on or near the surface of Earth. So when you throw an object into the air, guys already kind of talked about this. I've got an object here, and I'm going to throw it up. What's going to happen to this thing?
it's gonna hit it.
Canware. Is that, what do you mean? If it's going to go up, eventually it's going to come back down. Okay. That's part of it. What else? Yeah, Connor?
It's gonna hit its apex, so it's gonna hit like a velocity of 0.
So right here, there's going to be v equals 0. Okay. What's happening on this part of the journey? Sorry, you were talking first? Well, yes, we'll deal with energy 2 chapters from now. There's dynamics and then work energy. It's gaining potential energy, losing kinetic energy. That is true. I'm not writing it down. Luis. The velocity starts positive, yeah. And what's it doing on the way up? Connor.
Its acceleration is decreasing.
That's not true. Think about what you just said. Acceleration stays the same. Acceleration is not decreasing. What's decreasing, Connor?
Velocity.
So its velocity is positive and decreasing, meaning it's slowing down. Which you expect it to, right? At the top, it has to come to a stop so that it can start to accelerate in the other direction. To get from a positive velocity to a negative velocity, you have to go through 0, right? So eventually, there has to be a point in space where this thing stops moving. It'll only stop for an instant because as soon as it stops, it's going to start moving again. In this case, over here, the velocity is going to be going to be negative, and it's going to be increasing. If the velocity was positive and decreasing, and then on the way back down it's negative and increasing, which way does my acceleration have to be? It's be downwards or negative. It doesn't matter where you are as you're flying through the air, the acceleration is always, always, always pulling you back down towards the surface. That's why as you rise, you slow down, and as you fall back down, you speed up. What happens if you toss a ball on the moon? Has anyone seen the YouTube videos of the guys on the moon? Neil Armstrong, Buzz Aldrin, jumping around on the moon?
Like the moon has gravity, but if you throw the ball like too much force up, you're going to hit the moon.
Yeah, so the moon's got a lot less gravity than Earth does, and the reason for that is what? It's much, much smaller. The moon is actually roughly the same size as Mars. Mars is, we don't typically think about Mars being a small planet, but Mars is very small. The moon and Mars have a very similar mass. It is, I gave you the moon's mass, 7.35 times 10 to the 22 kilograms. These numbers are on your formula sheet. So that is a difference of almost 100 times.
How long would it take you to walk like around?
I have no idea. Well, we can figure that out.
It's calculatable.
I give you the radius of the moon. The radius of the moon is 1.74 times 10 to the 6 meters. It would take a while. That's 1/5 of the Earth's radius.
Okay.
It's pretty big. But its mass is 100 times less.
I don't know how heavy.
Because we can look at the effects of gravity. That's a great question. No, it's not an assumption. We know these numbers. And the reason we know these numbers is because there are relationships that you haven't learned yet in a field called orbital mechanics. You'll look at it in Physics 12. And that relates how long it takes something to orbit, the shape of its orbit, the mass of the two objects, one being orbited and the other orbiting, and their masses, and it relates all of those concepts together. So just by looking at how long it takes the moon to go around the Earth once, if we can figure out how far away the moon is, and we know how far away the moon is, we can really easily figure out the mass of the moon. We just work it backwards. But in Physics 11, I'm like, oh yeah, here's the mass of the moon, and then we use it to do stuff, which doesn't actually make a lot of sense, which is why that question's a really good one. We just worked it all backwards. A guy named Tycho Brahe in the 16 or 1700s, and Johannes Kepler. Kepler might be a name that you recognize. Those are the guys that developed orbital mechanics as we understand them today. I took a course on the history of physics, and I talk about them both in Science 10 and in Physics 12. And those, Johannes Kepler is a pretty awesome name, and he did some pretty badass stuff, so I've been doing it for a while. Anyway, that's how we know the mass of the moon. And it's the same way we figure out the mass of all sorts of these other objects, right? Even looking out at way, way, way out into space. We point the Hubble telescope out far enough, and we can watch these things orbit each other. We can figure out really easily, assuming we can see a couple loops to figure out a rough orbital shape and the time it takes to do that, and the distances they are from each other, we can figure out the mass of these objects. That's how we look at a black hole and we say, this is the mass of that black hole, this is the mass of this star. Because the physics is fairly simple. So on the moon, this whole thing happens the same way, but what's different about the moon versus the Earth? The acceleration is different. So what's that going to look like practically? Which leads to what practical result? The ball decreases velocity slower, which leads me to what? Connor? It's going to stay in the air longer, and it's going to go higher. In air that's not the word we want to use, because there's not a lot of that on the moon. I don't think there's any of that on the moon. I'll say stays up longer. goes higher. Should be a G, not a D. And falls slower. No, I'm going to ask a different question on Google. What you're asking about is what's a concept called escape velocity. You'd have to throw a ball at almost 2.5 kilometers per second. So no. But there are objects that can do that relatively easily. You can't, but we can build something that could. So what's the reason for this? The reason is smaller mass gives us less gravity. I even give you that value, I think, on your formula sheet. Yeah, I do. There it is. I'll say, we'll start using letters for this now. Little g moon. Little g is the acceleration due to gravity. I'll say g moon is equal to 1.67 meters per second squared. So almost a 10th. No, almost a 5th. Like 20% of gravity. And again, that's also down. So that's the acceleration due to gravity. Acceleration due to gravity is always acting down. What does that result in practically? As a ball is dropped from a height, what is going to happen to the velocity? And we want to sketch a velocity graph. So I've got my ball. This is going to feel a little redundant, maybe. Initial velocity equals 0. I drop the sucker. What's going to happen? What do we know is true? We know the acceleration is what?
For the Earth or from the
We're going to operate under the assumption that we're on the Earth, unless otherwise specified. 9.81 meters per second squared. Now, this is where things get interesting. We know that it's down. It has to be down. But what you call positive and negative in all of these problems is going to determine whether this value shows up as positive or negative. Which direction? In your labs, we called down positive because your graph went up and to the right instead of down and to the right. So for the sake of this, I'm going to call up positive, which means my acceleration now is going to be negative 9.81 meters per second squared. So what's happening to the velocity? Well, it's going to be increasing as it falls in a negative direction. What's this graph going to look like? Velocity is not constant. Acceleration is constant. My velocity starts at 0 because I'm dropping it, not throwing it. And what is a constant velocity going to, a constant acceleration on a velocity time graph going to look like? This is a VT graph. Sorry, that's V, this is T. There's a few different ways we can depict that. This is a velocity time graph. So let's do this. Let's set up a little table here. We'll have T, we'll have V. After 1 second, how fast is my object falling? Assuming this acceleration. Yeah, it's going to be going negative 9.81 meters per second. After 2 seconds, how fast is this thing going to be going? 19.62. Negative, yeah. After 3 seconds, how fast is that object going to be traveling? You've all got calculators. It's not my math. My math nines aren't allowed to use theirs. You guys can. After 3 seconds, how fast is audio going?
29
Yeah, man, come get with you. Back. So what's the value? Is it 29.43? Someone with a calculator? 29.43, okay. Okay. I don't need to do 4 seconds. I don't need to do 5 seconds. These things, how are these values, how did you find them? Or how would we find them? Dave, what were you doing in your head?
adding negative 9.81.
We were adding negative 9.81 every time. So, when I'm adding the same value, what's this shape of my graph going to look like? After 1 second, I went down negative 9.8. After another second, I go down negative 9.8. After 1 second, I go down negative 9.8. After another second, I go down 9.8. This graph is going to be a straight line because acceleration is constant. That's the only reason I was able to give you the lab that I gave you. Your second graph should look like a straight line. So if it doesn't, you've got some things to figure out.
Oh, about the lab, just a quick question. Like, I did another line of best fit, and I got another result. So I need to put the result that I had first, or can I use this one that is more accurate?
Technically, you can't have a best line of, sorry, you can't have multiple lines of best fit because best implies that it is truly the best. So you might have a couple lines of pretty good fit.
Yeah.
You could say then in your summary, my data was a little bit messy, so I drew a couple different lines that all could be considered to be pretty good fits. Here's what I got. Yeah, sure, include them both. That's fine. The cart's like it's unlocked. You just got to twist it to open them. Okay, so it's going to be a straight line on a VT graph. How about a DT graph? Sorry? This one's going to be curved. Yeah. This is the one that's going to be, it's going to give us our curved line. Because the velocity is increasing, the rate at which you're falling is going to be increasing, which means it's going to take less time to fall farther. So you're going to get this kind of dramatic curve downwards. In fact, you maybe didn't recognize it yesterday when you were graphing these things, but it's a parabola, and you're going to see that. Well, actually, you could deduce that already, because d equals VIT plus half AT squared. If you've taken pre-calc 11, this is a parabola where t is my x value and d is my y value, right? This is a quadratic function. So this is going to be a parabolic shape. So that's what that graph is going to look like. Cool? Flip the page. Okay, so now instead of dropping the ball, I'm tossing the ball into the air. What's happening to the velocity? Well, you've already kind of said it, so I'll rehash it for you. The ball is going to go up. You said it was going to slow down, stop for a sec, and then speed up going the other way. What's that going to look like on a VT graph? I'll go like this. See first page. 4. Explanation. I'm not going to make you repeat yourself. On a VT graph, what's it going to look like? On a VT graph, not a displacement time graph, a velocity time graph. If you're throwing an object into the air, what have you given it to start? You've given it an upwards starting velocity. Don't flip back, I'll flip back. You guys sit right here. It's tossed in there. So it has some sort of positive velocity that's going to be decreasing as it travels. Up to 0. So on a graph, that's going to look like something like this. I've given it some positive velocity. It's going to have to go through 0. Are those 2 points connected by a straight line or a curved line? Who said straight? Why, Manuel? Because the acceleration due to gravity is constant, so this is going to be a straight line here. Acceleration is constant. Straight line. Implies a straight line. Okay, so then what's going to happen? This point right here is when? That's a good question. Is that what it means? This is a VT graph, not a DT graph. This is where I first threw my object up. It has a positive decreasing velocity, and then now the velocity is 0. So where is my object in the world? Or what's happening to my object now? James? It's at the top of the throw. Right here is the top of the throw. I'll go right there is the top of the throw. So then as our object now turns around and starts to fall back down, what's the rest of this graph going to look like? Has acceleration changed at all? So because the acceleration hasn't changed, the acceleration is constant, this line has to continue on with the same slope. How do we know when the object is back where it started? Connor.
Because it would have gone the same, it would have gone the same amount of time with the, like the reciprocal velocity.
Not reciprocal velocity. It's opposite but negative. Reciprocal means I'm flipping a fraction.
Right.
It was 6, now it's 1/6. You don't want that. If it was going 6 meters, if my initial velocity was 6 meters per second, when the object comes back down, the velocity is going to be -6 meters per second. That's how I know this thing has come back to where I started it from. And you were talking about the time piece here too. Time up. This is going to be time down. These two times, I'll write it down here, T up equals T down to reach the height it started from. So, follow the result. Thank you, Connie. The speed graph's a little weird. The difference between speed and velocity is what? Velocity is a vector. Speed is a scalar. Velocity is a vector, speed is a scalar. Which means speed does not have a direction, which means speed is never negative. So a graph of a speed time graph is going to look like this. The object has speed, it falls to 0, now it's gaining speed again as it comes back down. It rises to no speed, and then it falls and speed increases. The difference between speed and velocity, this guy's a vector, this guy's a scalar. Scalar means can't be negative. And the last piece here is this. What is a displacement graph going to look like? If I threw this thing from ground level, we're going to start here at 0. I'm throwing it up, so which way is the ball going to go?
Like the first thing is 0, the final result, so definitely the here going to be up and then down to the same point.
Yeah, if I'm throwing it from ground level, yeah, it's going to go up, reaching some maximum height, and it's going to come back down. And this shape is supposed to be, it doesn't look like it, but it's supposed to be a parabola, which you spent probably way too much time in Pre-Calc 11 graphing. And the reason for that is because my displacement is equal to my initial velocity times time plus 1/2 my acceleration times time squared. Because I'm graphing d versus t, d is my y value, t becomes my x variable. That is a quadratic. It's going to look like a parabola every time. Which is why when you throw an object, it doesn't matter what the object is, assuming you can ignore air resistance, it's going to follow a parabolic path. The parabola might be short. If I throw this, if I throw an orange at Luis, I'm not gonna because I want to eat this later, but if I throw an orange at Luis, I could either throw it pretty shallow, but it's going to curve up and then arc back down, or I could lob it to him and it'll go really high and really low, or really high and then come back down, sorry. It doesn't matter how drastic the shape is, it's always going to be parabolic because of that relationship right there, which is kind of cool. Okay, flip the page, let's keep going. Yeah, Manuel. Yes, gravity affects light. Gravity bends light. Actually, that's not true. Gravity warps space-time and light travels in a straight line. I'll show you a video. That's the video I keep talking about.
You gotta show us that.
I will, but it's not in this chapter. It's in the next chapter. Okay, so here's what you need to remember. Let's draw this thing. The acceleration is equal to negative 9.81 meters per second squared on Earth, everywhere. That's and the other piece here, I used to have a whole lot more in here, and I don't actually think it's useful to give you, so I'm not going to give you all of it. I'm just going to give you these first two pieces. The velocity at the top of a throw is always going to be 0, because that's the top. It's not going any higher. It has to be 0 there. In the past, I did a lot more that I've filled in here, and I think it ended up just being more confusing than it was worth. So let's just jump into some examples here. I've got a ball tossed vertically upwards at 15 meters per second. How high does it go? Nothing has changed how we approach these questions. The only thing that has changed is the implications of the wording. So like before, I gave you questions like, so this object starts at rest, and then this happens, or the object was moving and comes to a stop. The language there tells you that at rest, initial velocity is 0. Coming to a stop means final velocity is 0. The language gave you something to assume. Here, if a ball is tossed vertically upwards at 15 meters per second, what can we assume? What's the first thing we can assume? The first thing we can begin, because this thing is tossed, tells us the acceleration is
9.81 or
negative 9.81 meters per second squared. Manuel.
You could assume that the max height is the same as when velocity is 0.
Absolutely. Those are the two things that it becomes really important that you're able to pull out of stuff like this. that the accelerator, because the thing's tossed on Earth, assuming it's, if I don't tell you otherwise, assume it's on Earth, that gives you the acceleration, and the height it reaches, at that height, the final velocity is going to be 0. So we can draw this thing, make our life a little bit easier. This thing's going to go up. We want to know, Manuel already called it max height equals question mark. We've got our acceleration, we've got our final velocity. What else do we know? We know our starting velocity. Our starting velocity is VI equals 15 meters per second. Is that enough information to figure out how high the thing goes? Oh, and for the sake of this question, I'm calling up positive, which is why my acceleration is negative. So then the kinematic equations are still the same. Which kinematic equation is going to relate VI, VF, A, and the maximum height? If you don't have them memorized, having your formula sheet out is never a bad idea. While y'all are digging for it, I heard Zaid say VF squared equals VI squared plus 2AD. VF, VI, A, and the max height is that D value that I'm looking for there. This is the kinematic equation we're going to use. So once we've set it up, we write down our equation, we fill in the values, and we solve it. The units all work, so I don't have to do any conversions there. So I'm going to get 0 is going to equal 15 squared plus 2 times negative 9.81 times D. Well, 15 squared is 225. And I'm going to subtract it over, so I'm going to get negative 225 is going to equal 2 times 9.81. It's going to be negative 19.62 times D. Divide both sides by negative 19.61, and I'm going to get my displacement is equal to what? 11.45 what? Meters. And I said up was positive, and my final result is positive, which means my object is actually going up, so that's great. How long does it spend in the air? What am I looking for? How do I solve that? I've got VF, I've got VI, I've got A. I don't want to necessarily use what I've just found here. Is this rounded at all, Gerkird, or is this exact? This is rounded. Okay, so we don't want to use it if we can avoid it. So I've got VI, VF, and A, and I want to find T. So which one of you three gentlemen just said it. Which formula am I going to use? VF equals VI plus AT. VF is 0, VI is 15, plus negative 9.81 times T. Subtract 15. So what's T? It would be in seconds. Did I answer the question? What did we find? We found how long it takes to go up. So this is the time to the top. Total time, which is what I was looking for, spend in the air, is going to be T top times 2. 1.53 times 2, which is, I guess, 3.06 seconds. This piece right here is only true when? Sorry, Luis?
When time stops not 0.
No. Because then that would still be true, because that means I haven't thrown the object. Manuel. Zaid. This is only true when an object starts and stops at the same height. So if I'm just standing on the ground, I throw the ball up, it's going to take the same amount of time to go up as it did to come back down. If I'm standing on top of the school and I throw the ball up and it falls off and I don't make it and it goes over the edge of the school, it's going to continue to fall. So then in that case, total time is not going to be time to the top times 2, because you're going to have to add all of that extra time to get back down to the ground. This is only true when an object starts and stops at the same height. We cool with that? With all this? Okay, flip the page, let's do a couple more, and then I will release you to work on some of this stuff yourself. Stones drop from a bridge, falls for 2.35 seconds before hitting the water. How high is the bridge? What have we got going on here? Connor?
You have a time.
I have a time. T equals 2.35 seconds. What else do we know? Acceleration. Why do we know acceleration? It is on Earth, but what's it doing on Earth? It's falling. This word right here gives us that acceleration is equal to negative 9.81 meters per second squared. Do I give you on the formula sheet? I gave you 9.80. It's not technically 9.80. It's 9.08 or 9.806, I think. So this is a rounded value. Even if we start using 9.8, that's totally acceptable. You're going to see a few different values here. It's because it either rounds or it gets more. We can either round it to a particular point or it gets more exact. I like 9.81. What else do we know? VF is 0? You sure? Let's say this way. I drop a stone from a bridge and you're in the water. Does that stone have 0 velocity when it hits you? No, it's going to hurt because it has lots of V. So what is, we need one more piece of information here. What's the implication? Why is the V initial 0? Sorry? Because I'm dropping it. It was in my hand, and I went like that. I didn't throw it down at you, Luis, in the water. I just dropped it. So this word right here gives us that V initial equals 0. So now I can draw this thing. Here we are on the bridge. There's water going on down here. Let's make it fun. Here's Luis. Bam. There he is swimming. No, I didn't say that. No. No, orange is not going to kill you, Luis. Maybe you're hungry. I'm just tossing it to you because I don't want to walk over. You're just... You know what? That's okay. I'll hurt someone else next class. Don't take it personally. And we've got a rock. And we're going to drop it. And I want to know what that height is. Well, I've got VI, I've got T, I've got A. Which formula am I going to use to relate those three things together? And give me the height. You like your carrot? You betcha. And the beauty of this equation here is VI is 0, which means this whole term is 0. So D is going to equal 1/2 negative 9.81 2.35 squared. What's the maximum height of that bridge? Negative 27.09. What have you just found? What did we find? We've not the distance. We found the displacement of the object, and our object fell down, so the displacement should be negative. That wasn't what I specifically asked for. I asked for the height of the bridge. I didn't ask for the displacement of the rock. I asked for the height of the bridge. So how are the height of the bridge and the displacement of the rock related to each other?
The rock was up, so it goes down, so the filter is like the height.
The height is just, yeah, it's just going to be the 27.09. The height's not negative. The displacement of the rock is because it was falling. But the height of the building, or in this case the bridge, is just going to be 27.09 meters. So if you ever want to figure out how tall something is and you don't actually have any device, like a ruler or whatever, to measure that would be sufficient length, you just need an object to push off and a stopwatch. And you can very easily figure out how tall something is. This is one of the first labs that we do in first year physics at U of V and a couple other universities that have a sufficient height. We go up to the top of the clock tower, we drop marbles, figure out how tall that clock tower is. All you need is something to throw or drop and something to time. How fast is that stone going to hit Luis? Oh, yeah.
Would it also affect where you drop it from? Like, if I drop it from like my head, right?
What do you mean?
Like, where I'm letting it go from there, let it go from like the edge of the bridge to find the height.
Yes, if I'm finding the height of the bridge, yes. Yeah. Yeah. How do we figure out how fast that thing's going when it hits Luis? Oh. I want you guys, here's what I'm going to give you. I'm going to give you some homework that I want you to do over the weekend. I want you to do question number 1. I'm not going to give you as many as I would have if we had class. I want you to do question 3. I want you to try 4. And I want you to try number 8. 1, 3, 4, and 8. Oh, you want the kangaroo too? You can do the kangaroo too if you want. 7 is optional. Have a good day, guys. Enjoy your weekend. I'll see you on Monday. I hate short blocks. I thought I had 5 more minutes. Yeah, I'll call. Yes, who care?
You know how we made the tangent lines and figured out 5 points?
For which lab?
For the lab that did yesterday?
Oh, constant acceleration, yeah.
Oh yeah, that. So for the instantaneous velocity, how the slope is vf minus, not vf, I'm sorry, y2 minus y1.
Yeah, over x2 minus x1. Yeah, rise
so
over
I
run.
have to use 2 points?
For the tangent lens, yes.
And I can use
Any
that
two.
with 5 points. Like,
So what you've done here, I gave. So see you later. So at this point, you draw the tangent line.
yes.
So there's my tangent line. Now we find 2 points on the tangent line to find the slope.
Oh.
And you do that 5 times.
I don't use this point,
No.
but the 2 points on the tangent
Yes.
line. So that means I have like 10 points.
Technically, yes.
Okay.
Well, pairs of 5 pairs of 2 points.
I did it wrong, then I was looking for if the gravity thing equals 921 and I got 5.
Yeah, there's a bunch of you that did that.
Okay, thank you.
No, you're here first.
So I find the point, right? And
Yeah.
I use that, and then
Yeah.
that.
Yeah.
Okay.
Yeah. No, it's good. Luis.
Yesterday when I arrived home I was trying to do like the best line of best fit.
Yeah, I mean, with your data,
Yeah.
it's hard to do a good
Mhm.
to figure out what the actual best line is. What was your second one? What was the slope?
Like the slope was 10. So
Oh, that is better.
yeah.
Well, it's more reflective of reality.
Uh-huh.
Yeah. So if you did both calculations, I want to see.
I did 3.
You did 3. What was the third one?
The third one was I think 8 or 7 something.
Okay.
Like that.
So, is all of that on? Did you erase it every time, or are all 3
No.
lines on there?
Yeah, the 3 lines are there. So,
Okay, cool, perfect. Yeah, that's fine. And then you can talk about it in your summary. Then the thing you need to talk about in your summary is why it was so hard to draw that line of best fit.
Mhm.
Like, why was your data so all over the place? And I'm willing to bet part of that is
I think
the measuring.
yeah,
The measuring you guys did, I'm willing to bet was part of the problem.
yeah, probably.
But yeah, no, if you did all 3 calculations and they're on the graph, that's awesome.
Okay.
Sweet. No worries. Have a good weekend.
Hey, did you know that we are required to cover for people during our press?
What do you mean we're required?
I got told on that week.
And you've been ordered?
Huh?
And you've been ordered?
I've been told that Abe is away for
Yeah.
a month, and then she asked me to cover by directions of phone.
Okay.
I said, do I have to? Because I'm really trying to avoid going to a classroom with COVID, right?
Yeah.